Start coding. Okay. So, welcome back students. So, basically we are discussing several strategies or several guidelines based on functional group based interconversion, and today we will be trying to continue our discussion on functional group based strategies, and here we will be trying to focus about our guideline 4, and the guideline 4, if you go back to our earlier lecture, it basically focuses on strategic use of protecting groups in functional group interconversion. Now, in this subsequent lecture series, we will try to emphasize much more on what are protecting groups and how these protecting groups will help you in designing a suitable pathway. Definitely, as you say that our main discussion will be focused on different problem solving approach. We will try to focus on particular protecting groups and how these protecting groups will help us to design a efficient pathway. I said this particular compound which is having 1, 2, 3, 4, 5, 6 CH2 or methylene, one end is having CO2 ET and CN. This target molecule was given to you, the starting material was something like this 1, 2, 3, 4, 5, 6. I said if this chlorohydrin kind of compound 1, 6 this is giving you a starting material, and you have to basically prepare this compound. Now, if you try to correlate, the 6 CH2 groups are similar in between, only thing is one end you need to have a CN and this end you need to having a CO2 ET. Now, the straightforward way to solving this problem is basically how you can do it. You can think about converting hydroxy to a cyano or converting the chloro to corresponding cyano and then converting this OH to, but the main thing is this free OH probably is not compatible with some of the reactions we will be talking about. So, free OH basically it is having acidic hydrogen. So, you cannot use base or some other reagents, like you cannot generate a Grignard species from a free hydroxy group. Like I want to introduce a Grignard here, you want to generate a Grignard here which can be quenched with this carbon dioxide to give the corresponding carboxylic acid, and then you can come up here. But the point is, if you have a free OH, you cannot generate a Grignard because the Grignard will be immediately quenched by this alcoholic acidic hydrogen. So, in those cases whenever you have a labile group, labile functional group which can be easily reacted under acidic condition or basic condition or other conditions, then you need to make this functional group as inert as you can. Now, inert means the functional group is active, you need to basically put some protecting group here. Now, that is why the need of protection group was felt or required. In reality, protection group is basically nothing, you are putting a mask or called a masking. Basically, you are masking the alcohol functionality with a protecting group, and once the synthetic transformation or FGI was done, you basically remove the protecting group, which is also can called as a demasking. So, this terminology sometimes helps. Now, coming to this particular problem, I said that the alcohol is free, so you need to use a protecting group. Now, alcohols normally was protected as it is corresponding tetrahydropyranyl ether by a suitable reagent named as DHP. Now, DHP is this reagent, and DHP, if you are having a react with DHP with alcohol in presence of a catalytic amount of mineral acid or para-toluene sulfonic acid, initial thing is you get a positive charge here. So, DHP in presence of acid basically gives a positive charge here, because this positive charge is stabilized by this oxygen and hydrogen is adding here. So, basically it is like this, you get a positive charge here. Now, this positive charge is now quenched by this corresponding oxygen lone pair of this alcohol. The alcohol is now protected as it is tetrahydropyranyl ether is called ROTHP. So, dihydropyran has now protected. Now, this compound is basically nothing, it is like a cyclic acetal. So, cyclic acetal is basically acetal. Okay. So, now your free alcohol is now masked, and this compound is normally inert under certain conditions. Definitely it will be cleaved under basic condition. So, we will talk about some other aspects of protecting group, but before that we try to solve this problem which was given to us. So, the initial compound which was given to you is a Cl 6 methylene in between 1 2 3 4 5 6 OH. We said this was put as a its dihydropyran was treated with a H plus. You basically will get first its THP. Okay. Now, we said we will do the next FGI. We are doing a magnesium treatment, magnesium metal, that will give you MgCl. Then we react with carbon dioxide followed by H3O or simple H plus treatment, that will basically give you a CO2H, means initial magnesium chloride reacts with carbon dioxide, it remains similar. Now, next your carboxylic acid need to be converted to the corresponding ester which was required. Now, you react with ethanol and H plus, strong H plus. Now, this strong H plus will form a ester bond with this acid, as well as we will remove the THP. So, basically what we will get? You get CO2 ET in between 6 1 2 3 4 5 6 OH. So, THP is now removed, free alcohol is now demasked. So, only thing is for Grignard reaction the free alcohol was not recommended, that is why we protected as a with this corresponding THP ether. So, next what you need to do? You need to convert this alcohol to a its cyanide. You can basically do it by standard SN2 reaction, treat with tosyl chloride first. So, we will get simple SN2 displacement, you will get tosylate ester and react with sodium cyanide, you get the corresponding CN. So, this is your target molecule. So, only thing is the free alcohol was not recommended, that is what you are using a protecting group chemistry. Now, the point is protecting groups are always not recommended, because if you are trying to use a protecting group, your synthesis will not be step economic, because 2 steps you are adding extra. First you have to add your protecting group to the starting material to get a starting material with a protecting group as a covalent attachment. Then you do some reactions here, do some FGI, and then finally you have to remove the protecting group. So, 2 additional steps are often required in any protecting group whenever is used in your retrosynthetic pathway. That is basically the main drawback for protecting groups, but nevertheless protecting groups are widely used because you will find that sometimes the target molecules are so complex and it contains multiple functional group which is having similar activities. We will discuss some activities little bit later on. Before that, we will try to use a general conceptual analysis how protecting groups have been dealt with. In reality, I will give you a compound something like this. I say you are having a 1N-diol, and both the alcohols are having similar reactivity, because both are primary alcohol having similar reactivity, but selectively you want to use a FGI on this end by keeping this end intact. Then basically you need to use a protecting group by masking here. So, basically what we will need to do, you can use a simple protecting group by masking this end. Okay. Then you do remaining FGI whatever is required in your synthetic transformation. Now, the point is both the groups are having equal reactivity, how you can selectively protect with one functional group. Here basically you have to use a stoichiometric control. Stoichiometric control means that as both the groups are equally reactive, you are having two active functional group, two active FG. Now, you use one equivalent of PG or the protecting group. So, make sure the PG basically blocks one end of the active functional group, remaining one end remains intact. So, this stoichiometric control means your two equivalent is the two active part and you are using only one equivalent. Sometimes definitely you are having little bit of di-protected compound as your byproduct, that is a side product. But nevertheless this kind of reactions are very useful, and if both the protecting groups or both the functional groups are having equal chemical reactivity, like this case you are having both the case primary alcohol, things will be little bit simplified if you are having a compound like this. I will give you compound, let us say now this compound, if you see this compound is having 3 active functional group, is a 1 degree alcohol, 1 degree OH, this is a 2 degree OH and this is a 3 degree OH. Now, 1 degree alcohol are sterically less crowded, 2 degree little bit sterically crowded, but not as like 3 degree, and 3 degree alcohols are sterically highly crowded. So, in principle if you use one equivalent of protecting group, the reactivity pattern or reactivity is 1 degree will react first, then 2 degree, then 3 degree. So, if you use one equivalent protecting group, first primary will be reacting fast, okay. And then if you use another protecting group, you have now 2 free, either secondary or tertiary. Now, I said secondary is sterically less crowded than the tertiary. So, next protecting group will attack the secondary and then tertiary will be affected. Now, depending on which functional group you want to use in your next FGI, you can basically selectively tune that which protecting group you can use. Now, if your 3 functional groups are having similar environment, like all are 3 are primary, then you have to choose stoichiometric control, and if the protecting groups are different, like one is primary, one is secondary, one is tertiary, their steric environment is different, they belong to different steric environment, and in those cases you can basically control it through the steric crowding. As I said, the primary alcohol will be protected first, then secondary, then tertiary. So, we will try to figure it out some of the chemistry of the protecting group, and we are not going to do a very general discussion. During the problem analysis, whatever protecting groups are come into our discussion, we will talk about only those protecting groups. So, next problem which was given here is basically a target molecule is given to you having something like this. Now, if you see this molecule is basically a target molecule was given to you, and the starting material which was also supplied to you is okay. Now, this is a very, it looks a very simple transformation. What you need to do? You need to really do the CO2Me and CH2CH2I. If you reduce this CO2Me, it will give you CH2CH2OH. Now, this primary alcohol you can easily convert to it corresponding iodo by Apple reaction. The point is there are other OH group in between. So, if you just simply react with a lithium aluminum hydride, what will end up? You will get OH, CH2OH, CH2CH2OH. Now, there are 3 hydroxy group, 2 primary, 1 secondary, and selectively your target molecule contains only 1 iodo group at this primary. So, it is very difficult scenario. You cannot use simple Apple reaction, because then this will be also reacting, this also may react, but this is primary and secondary, probability is less, but this will be definitely not that much chemoselective. The only solution you are having that in the initial part, if you can protect this primary and secondary by some selective protecting group and then do the reaction here. So, the solution which will now provide is based on something like this. You have a primary hydroxy group, you have a secondary hydroxy group, and this part you need to do the reaction. Now, the primary and secondary, this is basically diol, this is compound 1, 2, 3, so 1, 3 diol. Now, your job will be quite simplified if you have a single chemical reagent which can protect both the primary as well as secondary. We will be using a reagent very simple, acetone. Now, acetone, as I know, as you know, all of you know, acetone can easily form ketal with 2 equivalent of alcohol. Now, here the 2 equivalent alcohol is, one is primary alcohol, one is secondary alcohol. So, what acetone will do? It will basically forms the cyclic ketal, which is now named as acetonite. It is named as acetonite in terms of chemical terminology. It is basically nothing, is a okay, we can write this acetonite structure in little bit more convenient way, which looks much more easier. It is basically in reality is a 6-member thing. Okay, now get the 6-member thing, and then your this part remains. So, what strategy we have observed here? We basically use a one equivalent of chemical reagent which can react with the secondary as well as primary, and then use LAH. LAH will not affect this acetonite protecting group. So, basically you have to make sure the protecting group does not affected by the reagent which you will be using for your FGI. So, get the reduction, and then next you do a Apple reaction which you have discussed many time. Apple reaction you basically use iodine and triphenyl phosphine, or eventually if you do not use Apple reaction, you do it a different way. You can do either Apple reaction or you can do a tosyl chloride pyridine, and then you can use 2-step sodium iodide, that also will give you a your iodide thing. So, now you get iodide, your acetonite protection will be remain here. Next you just need to remove this acetonite by treatment of H plus. So, next basically what will get? You get the this part will remain similar, and the alcohol will be now as it is, and your acetone will be removed. So, we have used a acetone as a strategically protecting group to mask the primary hydroxy as well as secondary hydroxy, so that these two hydroxy group remain inert during our functional group transformation. So, in this way particularly we will be using several protecting groups, and our next example will be focused on a similar kind of protecting group, and there we will be using some other chemistry. You will just observe how we will do it. We say target molecule is something like this, and the starting material which was given to you now. The initial target is basically does not have a active functional group. It is having a oxygen ring or tetrahydropyran ring, and is having a 2 methyl and tied to each other. The starting material which was also supplied to you having a alcohol functionality here. So, this alcohol if you can remove, that will basically give you the carbon hydrogen. So, basically in reality you need to do a deoxygenation reaction which was basically required from you. Now, as I said, we will be using a protecting group based chemistry. So, deoxygenation, this kind of reaction we will be discussing when you talk about redundant functionality. So, for the time being we will be using a different strategies. What will be doing the retro? The retro now will be based on a very conventional and classical retro. We will say that we will try to bring some functionality here based on this alcohol. We say that OTS, O-tosyl, tosyl is a very good leaving group, fine, and if you can replace this OTS through a suitable leaving group. Now, here you need to do a this, as I said, it may undergo a nucleophilic displacement reaction. Okay. Now, if you bring some nucleophile here, it goes up, it is a very good leaving group. Now, what nucleophile you need to use here? Because you need a carbon hydrogen bond. So, hydride might be a good nucleophile, and we all of you know that lithium aluminum hydride is a good source of a hydride. So, eventually your forward pathway will be now having the chemistry which is now we can formulate in this way. So, you are having this OH, you react with tosyl chloride, is this compound Cl, and actually by reacting with this tosyl chloride the alcohol is basically protected, is not it? The alcohol is protected. Now, what you do? You put a H minus, this H minus basically attacks to this tosyl and it goes up, entire tosyl goes up, and basically you get a methyl. So, it is a SN2 reaction. You are basically using a hydride source of nucleophile, and this is also a very nice demonstration. Now, if you can use a very source of nucleophile, you can use lithium aluminum hydride, even you can use sodium borohydride as a hydride source, you can use superhydride lithium triethyl borohydride. This is a very good hydride source, and in general the solvent was chosen as a THF, you can use it. Now, in terms of another useful conceptual analysis, this hydroxy group is now termed as redundant functionality, because the target molecule the functional group hydroxy was not required, but it was introduced to bring a hydrogen carbon bond and those kind of functional group which was in reality not required in the final target and has to be removed prior to access the target molecule is named as redundant functional group or redundant functionality. We will explore this redundant functionality a little bit later on. And so, in continuation of this protecting group chemistry, we will now try to give you a very simple problem. Now, this is basically a double bond, it is a double bond. We will again rewrite the structure. We put a cyclopropane here and is OTBS. TBS is basically a alcohol protecting group which is tertiary butyl dimethyl silyl. The starting material which was is a target molecule. The starting material which was given to you so this lactone. Now, if you see the cyclopropane part was there, this part is CH2O protected CH2O, something you need to introduce a extra group here you need to introduce, that is the only thing. Now, how many carbons you need to increase? You need basically one carbon is already there, you need to two extra carbon. So, now if you try to go back the retro pathway, we say that this compound can be prepared starting from, if we have this tertiary alcohol, you can simply do a elimination reaction. Okay. Now, if I say this compound can be easily prepared if you have this compound, is fine. Okay. And then now I say this will try to correlate with this. Now, you say lactones, this is ester basically, lactone or ester, if you react with one equivalent of methyl lithium, it will give you ketone. Now, we will try to explore the entire synthetic pathway. We basically having a lactone here, we react with one equivalent of methyl lithium, and we say initially you will be getting this methyl and CH2OH. Now, this CH2OH needs to be protected, that is why you put a TBS group, this is Cl and tertiary butyl dimethyl silyl chloride. This reagent which was used as protection purpose is a base which is basically a imidazole which was used, and you will get this as a OTBS and COMe, fine. Then you use another equivalent of methyl lithium, that will basically give you OTBS is there, and you get this tertiary alcohol OH, sorry, this is the methyl part, the methyl remaining methyl. So, actually you basically need to protect this CH2OTBS to make sure that this methyl lithium is acting as a base. So, whether this base can do some disturbance here, that is why this free alcohol need to be protected. Now, here you can basically convert this alcohol to its corresponding tosylate or mesylate, or just do a simple water elimination by tertiary alcohol, and you will find that you get the target molecule quite easily. So, basically by simple using of properly chosen protecting group, your synthetic pathway can be very nice and very demanding. The only thing is your protection has to be completed, and you need to remove the protecting group at a proper stage. So, two extra steps basically you are required. We will continue our discussion based on the protecting group chemistry when you come back in the next week. Till then, goodbye.